is medium temperature and low voltage pouring for PMN-27% PT crystal. I will start by introducing you with issues with PMN-PT crystal transducers in medium to low frequency applications. These applications include breast cancer HIFU transducers, which are from 200 to 400 kilohertz in frequency, and high-performance NDT transducers, which are from 100 kilohertz to 1 megahertz in frequency. First issue, not enough sensitivity due to electrical impedance mismatch. The capacitance of PMN-PT crystal is usually smaller than desired due to their limitation on thickness and element size, limited by bandwidths. Secondly, not enough output signal intensity due to lower coercive field. The coercive field of PMN-PT crystal is usually a quarter to half of that of PCT ceramics. What are the proposed solutions? Firstly, we propose increasing capacitance by increasing relative permittivities. The figure on the top left shows that crystal lattice under 4 mm left structure is easier to be shifted by AC pooling than MM2 middle than 3M symmetries, and these corresponding to 001, 011, and 111 oriented crystals. In short, AC pooling is easier to be introduced in 001 port crystals, making monolithic phase much easier to be induced in those crystals. Secondly, we propose increasing relative permittivity while reducing strain and cracks by elevated temperature pooling due to easier domain switching. The graph on the lower left shows the comparison between heated crystals of the heated elevated temperature, pooling elevated temperature versus pooling room temperature. The green curves of the hysteresis corresponding to the ones pooling at elevated temperatures. It has higher remnant polarization and higher energy stored in each curve. Thirdly, we propose increasing capacitance by stacking of PMN-PT crystals. This is still under research and will be published soon. Why we are choosing PMN 27% PT? The graph on the left shows the X-ray diffraction pattern of two typical peaks, 001 and 110 peaks of three compositions, PMN 27% PT, 29% PT, and 31% PT. 27% PT is what we are experimenting with. We take the crystal, put them into powders, put them under diffraction, and see that with the increase the degree of the peaks, the higher the composition, the higher of 001 peaks and 110 peaks, which is consistent with the theory. Now, 28% of PT to 32% of PT are generally considered commercially more acceptable, near MVP. The materials properties of 27% of PT, if they could be enhanced by satisfying device requirements by AC pooling, then 27% of PT or lower PT content of the crystal could be commercially accepted. This will lowering overall cost of making transducers. There are 4 conditions we proposed in this study. The 2 conditions on the left of the screen are poured under room temperature, and on the right of the screen are poured under 65 degrees Celsius due to ease of fabrication. First condition, pouring under 25 degrees C and 410 volts per centimeter for 10 seconds. RT-DCP. Secondly, pulling on the alternative current of 0.1 Hz of square wave plus minus 410 volts per centimeter for 3 cycles on a 25 degree C. We call it RT-ACP. Moving to the right side of the screen, pulling on the 65 degree C and 205 volts per centimeter for 10 seconds. We call it MT-LV-DCP. And then pulling on the alternative current of 0.1 Hz of square wave plus minus 205 volts per centimeter for 3 cycles under 65 degrees C. We call it MT-LV-ACP. Let's look at the transducer fabricating and testing methods. First of all, crystals of different pulling conditions will be manufactured into single element transducers corresponding to 200 kilohertz with a typical application of the breast cancer treatment. They have 1 matching layers and 1 backings. Those transducers, together with a hydrophone, we put under water in the water tank, 20 millimeters apart. The transducers would be connected to a Olympus ultrasound pulse receiver, which is then connected to a oscilloscope. The oscilloscope will generate the waveform that we needed for measurement of minus 6 dB bandwidth and sensitivity. Here are the results corresponding between pulling conditions and materials properties. We are looking at 4 different pulling conditions on 1.7 millimeters of the crystals. The materials we're comparing to are relative permittivity, dielectric constant, resonance frequency, anti-resonance frequency, electromechanical coupling coefficient, piezoelectric constant, D33. As you can see, if we are comparing the columns down, AC pulling could improve relative free permittivity by 19% on 25 degrees C and by 16% under 65 degrees C. It could also improve effective electromagnetic coupling coefficient by 6% on 25 degrees C and 65 degrees C. AC pulling could also improve D33 by 13% under 25 degrees C and by 24% by 65 degrees C. Compared to RT DCP, MT LV DCP increases D33 by 2.3%, and with the same comparison, the MT LV ACP, or the elevated medium temperature pulling with a lower pulling voltage, will increase D33 by 13%. Both at the cost of increasing tangent delta or dielectric loss. Now, looking at the impedance spectrum comparison between RT-ACP and MT-LV-ACP on 1.7 PMN-PT crystals. The graph on the left shows that the impedance frequency profiles under 2 conditions are pretty similar, indicating pulling saturation is reached under each condition. The graph on the left shows the resonance frequency and anti-resonance frequency of 3.4 millimeters are half the value of that in 1.7 millimeters, confirming the uniformity of frequency constant across different samples. If we are looking at the transducer properties, which corresponds to the conventional pulling method, which is RT-DCP, and that of the best pulling method that we obtain from the materials properties, which is MT-LV-ACP, we learn that in terms of received field voltage response, M0, RT-DCP single crystal transducer achieved M0 of 45 millivolts. MT-LVACP transducer achieved M0 of 54.8 millivolts, an increase of 20%. In terms of minus 6 dB bandwidth, the former give a 49%, whereas the latter give 54.6%, a 12-point of increase. If we consider the standard frequencies between the two transducers, they're pretty much the similar. This is because the standard frequency of the transducer is usually determined by elastic properties of the piezoelectric materials and transducer configurations. Here are the conclusions. 4 different porting conditions are experimented on 001-oriented crystals, and AC porting can be significantly enhancing the key properties related to transducer performances. It is also found that the porting under 65 degrees Celsius with half the porting voltage of conventional porting can only improve piezoelectric properties, but not so under ACP, but not so much under DCP. Overall, the best conditions on the materials achieved were MT, LV, ACP, resulted from the combined effect of inducing monoclinic phase and facilitating domain wall movement. Lastly, when made into 200 kilohertz of transducers, minus 6 dB bandwidth and sensitivity have all been proved by the ACPs. Thank you.